All right. Last week I shared this with you, which is a program, uh, the industrial talk from Intel. So if if you're interested, you can join the online lecture. I think it is a good opportunity to you to, to get uh, some information, from the industry. On the this is very related to our course, and on IC design industry and semiconductor industry. So it's is the introduction to the IC design or semiconductor industry. So you can register from this link or the QR code. And also there will be another one. This is a series done by Intel every year. They call VLSI Bootcamp, which is online also, right? Which is good. So I share in the group. So it's a series starting from January, but you can select which part you want to join, and you will get the certificate from Intel. The one that is very related to our course is the first one, January register transfer level, or RTL. So we will use this technique, in designing the digital circuit. So you can learn from the industry as well. Why is it important? Yeah. So the number of participant is limited, to 100 only. So if you are interested, so you can register. It's online and this is free. Okay, so it's good. Now start with today we will continue with what we have learned last week, which is chapter 2. All right. So last week we have learned how to model the digital circuit using HDL, right? So we have learned, I think, this 2.1 and 2.2 already done. We have learned the Verilog syntax and the modeling style. So today my plan is to look at how we write a Verilog code or use the Quartus Prime software to write the Verilog, to try to write the testbench and do the verification and simulation. Okay, so because this is online, so let's take this opportunity to learn the software. I think it's good because you can do this on your computer, right? And I hope that you have installed the software already on your computer. And also we have learned the Verilog modeling style. We have 3 modeling styles: data flow modeling, behavioral modeling, and structural modeling. So we have discussed a lot last week, how to write a Verilog code by using this modeling style, either one or combination of the modeling style. So today, let's straightforward. I think it will not take too long to learn this, about and half hour should be done. Okay, so let's okay, this one I think you can do on your own. Let's go to this. Yeah, recall the example that we have done in chapter 1. Okay, so how we write the Verilog code to model this this circuit, and how to write the test code or the test bench to test our design whether it's working or not, right? So if we have this so we can model using the best way is to use the data flow modeling, because we have the equation, right? This is the equation. Or you can write the code using the structural modeling as well, because we have this circuit already. Okay, and then we will try to simulate, do the simulation, write the test bed and simulate the code, the design, and see whether we can get the output that is similar to this truth table or not. Right, now let's start with writing Verilog code. Okay, so if you have the equation like this, so you can write the Verilog code, of course, by using our Quartus software. So you can launch Quartus, okay, from your window. Okay, when you launch the Quartus, you have this this screen. So in your case, if this is your first time using Quartus, so you will have the empty screen and not recent project. You don't have this list, right? So this is the interface, the Quartus interface that we will use the whole semester, right? So when we want to write the Verilog code, so of course we need to create what we call a new project. So how to write or how to create a new project? So very easy. You can use this what we call the new project wizard, or you can go to here, file, new project wizard, or new this one, new project wizard. Okay, click this, and this is the wizard. Okay, click next. This is very important, the first one, where you want to save your design. Okay, by default it will save in the install folder. Okay, so my advice is that you create a new folder to save your project. Okay, and it should be in your C drive. Okay, in my case, I have one specific folder named Quartus, and we will create a new folder for this particular project, right? Because later on, when you have a project, it is better to have their own folder for one project. So one project, one folder. Yeah, you don't mix many projects in one folder, right? So in this project, for example, the project name is example 1. Okay, so we have the directory example 1, or folder example 1. Okay, so in Quartus, the folder is called directory. Yeah, so this is the directory or folder, and the name of the project, let's call this my design 1. Okay, click next here, and go for empty project, right? Because this is a new one, so we create from the empty project. Click next, add file. Just skip this because we don't want to add or attach any file to the new project. Okay, unless this project you want to have any other design, like for example other IP or whatever, right? So you can add that file, but in this case this is a purely new project, so no need to add any file. Click next. Device, if you have the hardware, so you need to select the hardware. Hardware here means the FPGA board, right? In our case, we don't use hardware yet. We just want to simulate the design using the software as well. So just click next, such that the Quartus will select the hardware automatically for you. Okay. So if you want to use hardware later on, for example, for your final year project, so this one is a must. You need to select the correct hardware, because there will be a lot of devices that you can select from. Okay, in our case now we click next. This one no setting, next. So this is the summary of the setting. Okay, click finish. Okay, after it is done, so you can see here is at the project navigation window. Okay, if you can see that, so this is called the project navigation window, right? And you can see that this is the design name. Okay, the project name is My Design 1, right? Now we cannot write anything yet, yeah, because there is no Verilog file is created yet. So what you need to do is you need to have a Verilog file, and you need to create a new one. So go to File, select New, or you just select this button. Okay, New, and when you select that, you will have this option. There are a lot of options actually. Like for example, if you want to create your project using a block diagram, okay, this is the selection. Or you have want to use VHDL. This is the file. In our case, we use Verilog HDL file. So click this, click OK. Now you can have this text editor that you can write your Verilog code. Okay. So now we can write the code already. Okay. So right here. Right, this is the design that we want to design, right? So to write the code, of course, you start with module, and you can see that the color of the text, yeah, is blue. And if you write anything else, like for example, My Design, okay, you can see that the color is black. All right, so this means that My Design is not a Verilog syntax or Verilog keyword, right? So in Quartus, the Verilog keyword will be in blue color, and if for the other text, yeah, will be in black color, right? And for number will be in red color, right? Again, when our project name is My Design 1, so our module name must use the same name. In this case, is My Design 1, right? And remember, when we want to write Verilog here, after we have the module name, so we need to list the port. Yeah. So in this case, we have port is this input D1, D2, D3, and A as output. So just write D1, D2, D3, and A as the output. Okay, don't forget to put semicolon. Input, you see it here, input is Verilog keyword, so it is in blue color, and D1 is our word, yeah, so it's in black color. So we have input D1, D2, D3. We have one output, which is A, and now let's use the data flow modeling, because we have the equation, right? So again, we need to use assign keyword for continuous assignment, assign continuous assignment, right? So A equal to D1 n. Okay, so based on this equation, D1 n, D2 or D3, we have close the bracket, or D2 and D3, right? In this case, okay, so it should be done. And module. After we have this, what we need to do is to save our Verilog code. So to save is easy, straightforward. Press this save. The default name is my design 1, and we need to use this name. Okay, click save. Right, is this done? Now after that, we want to check the design, whether it is correct in terms of syntax or not, before we can synthesize the design into the logic. Okay, so in this case, you have two options. One is to use this, or you can go to processing, start analysis and elaboration, or you can start analysis and synthesis. So for the first check, I think this one is the best option, because this is fast to check the syntax, right? Or you can use the shortcut here. Okay, same thing. So click this. Wait for a while. So again, this compilation is depend on your computer speed. Yeah, if your computer is fast, so the process will be fast. If your computer is slow, so the process will be slow, right? So in this case, we can see that we have 0 errors, one warning, which is okay. Actually, this warning is not caused by the design problem or whatever, because this one is actually because we use the light version. Okay, the software is light version, so it's just a warning saying that if you use the light version, you cannot have the setting to manage your processor. For example, if your processor has 10 core, so this Quartus will use all that 10 core, so you cannot use the resources, microprocessor resources, for other job. Okay, but this is okay for us. So one warning is good, actually, no problem. It is not because of the design. Okay, 0 errors, this is good. But in terms of I mean, this is in terms of syntax. Yeah, we don't know yet whether the design is correct or not, unless we do the verification to check the input and output, right? And we compare with the truth table, and if it is equal to what we have in truth table, then we can say that the design is correct, right? So in this case, this is just saying that, okay, your code is clean, is good for now. Now we need to check whether this design is correct or not. All right, so how to check? We need to write the test code and do the simulation, and we will see if the input that we provide to the design like this, and we should have the output at A like this, then we can say that the design is correct. Okay. And also when we have done this, analysis and elaboration or analysis and synthesis, actually we can check the circuit that this code will be synthesized to. To do that, you can choose the tools, Netlist Viewer, and go to RTL Viewer. Okay, click this. Okay, so you can see the gate that is created, the circuit that is created by the Verilog, based on the equation that we put in. Okay, and let's see whether this is correct or not. So to write the test code, what you need to do is that you need to create a test bench. Okay, so what is test bench? Test bench is this. Okay, so if this is our design, so our module will be this. Okay, let's call this my design 1, right, in our case. So our module now has 3 inputs, 1 output. Okay, now what we need to do is that we need to put this design into the what we call a test bench. So this is a test bench, right? And we need to create a new input, to put in the input, to put the input to our circuit, and we will observe the output at A. For example, if we have 0, 0, 0 here, what is A? If we have 0, 0, 1 here, what is A, right? So we can do that by writing a code. So to write a code, this is a code. Okay, so I will explain this by using Quartus. I think should be easier than this one, right? But first thing is that you need to think that, okay, you need to write a new code, a new module, just like we create a new module, we call it a test module. Okay, and you need to instantiate or call your design in that new module, right, before you can test. Okay, so in the test code, what we need to do is that, again, here you need to create a new Verilog file, new Verilog. Okay, so a new one. So you want to do this, want to create this. Now in the test bench, what we need to have is that, before we create a module, you need to specify what we call the time scale. Okay, because in the simulation later on, we will simulate the output, give the input and see the output relative to time, right? So it's something like this. Okay, if this is a graph to show the timing diagram of, for example, this is D1, this is D2, this is D3. Okay, What we want to do is that, for example, the first 10 nanosecond, what we want to see is that, let's say for example, in this case, D3 equal to 0, D2 equal to 0, D1 equal to 0, means that all of this are 0, 0, 0, and we want to see A, what is A, right, either 0 or 1, and then at or from 10 nanosecond to 20 nanosecond. So the time is depend on our design, yeah. So if you want to change the value of the input every 10 nanosecond, so it is 10 nanosecond. If you want to use other value, then should be no problem, right? So this is just an example. For example, at D3, you want to change this to 1, right? D3 is now changed to 1. D1 is still 0. D2 also still 0. So what is A, for example, right? So you can see that now the simulation is now relative to the time. Okay. So also the code that we want to write later on must be based on time as well. Okay. So we need to define the what we call the time scale of the simulation. So how to define the time scale? The answer is by using this keyword. So first, if it is very small here, how to show you? I don't know how to call this this symbol on your keyboard, but when you see your keyboard layout, yeah, let me show you your keyboard layout. Okay, can you see this keyboard?
Yes, can.
Yes, doctor.
You see this? This is the symbol that we use. You click this, right? So this is a symbol. Here, this one, yeah. Don't use this one. Not this one. All right. And you write time scale. Okay. Followed by the what we call the time unit. In this example, I use 1 nanosecond. I will show you. I will explain later on what is meant by 1 nanosecond here, and followed by slash another 1 nanosecond. Right. So first 1 nanosecond. The first 1 nanosecond representing the time unit of our simulation. What is time unit? Time unit is this. When we write in Verilog later on, when we want to refer to time, we use this. This we're not writing like 1 nanosecond or 2 nanosecond after that in the attachment. Okay, because we need to define the time unit here. So when we define 1 nanosecond, means that our 1 unit time is 1 nanosecond. Later on, when we write time in Verilog, to refer to time is using the hash symbol followed by the number. So this means that 10 time unit. So if we define 1 nanosecond here, means that 10 here means 10 nanosecond. 100 here means 100 nanosecond. Okay, if you define 1 nanosecond as unit time. But if you define, for example, 10 nanosecond as a unit time, as 1 unit time, meaning that when you write 10 here, the time is actually equal to 10 multiplied by 10 nanosecond, which is 100 nanosecond. Okay, I repeat. When we write the time unit here, means that 1 unit time is equal to 1 nanosecond. All right. Later on, when we write like this, or like this, 20, meaning that the actual time is actually 20 multiplied by 1 nanosecond, which is equal to 20 nanosecond. When we write 40, it means that 40 multiplied by 1 nanosecond, which is represent 40 nanosecond. Exactly, it's simple. But when you write like this, 10 nanosecond for 1 unit time, meaning that this is 20 multiplied by 10 nanosecond. So the actual time is actually 200 nanosecond. When you write like this, it means that 40 multiplied by 10, which is 400 nanosecond. You get what I mean?
Yes.
Okay, so it's straightforward. So the first one is called time unit. The second one is called a precision. Okay, the first one is called the time unit. The first one, time unit. The second one is called the precision. What is precision? Precision means this. Right? So when we do simulation, when we run simulation, what happens is that our computer will evaluate will read the input and produce the output. So how frequent the software need to do that, the simulation software need to do that, is depend on the precision time. Okay, for example, if we set 1 nanosecond as precision time, that means that the simulation software need to produce the output every 1 nanosecond at the time timing diagram. So in this case, if we have a 10 nanosecond like this, okay, so every 1 nanosecond here, so actually the software will read the input and produce the output. 1 nanosecond, okay, this is 0. 2 nanosecond, the output is 0. 3 nanosecond, the output is 0 until 10 nanosecond. So every 1 nanosecond, the software will check and produce the output. That is called a precision, right? So in our case, we will use this setting, means that our time unit is 1 nanosecond and precision 1 nanosecond. Okay. And after that, we need to write the test code. So the test code is just another module, but this module is used for test the design. Okay. So now just like we create a Verilog module, start with module, give it a name. So let's call this my design 1 testbench TB. Okay, let's call something like this. Okay, the port list is empty, no need to have the port, because the simulation code we don't have the port. Actually, this is the input signal, not the port. All right, just a signal. Also the output here, also the signal, not the port. Okay, so we not don't need to put the port list. Now, do we have something here? No. Okay. Oh yeah, this is good. So what we need to do is that if we design a new module, new circuit, this must be input, right? This must be output. But in test bench, this we will not declare as input, but we declare as rack. All right, remember the input of the test module, the test bench will be declared as rack, and the output will be declared as wire. All right. Okay, for that reason, so we will use rack to declare D1T. We name this one D1T, D1 test, or you can use the same name, doesn't matter. Yeah, you can use D1 also, but in this example I use D1T, D2T, D3T. Okay, done for the input of the test code. Yeah, and the output of the test code must be declared as wire, so the name is AT, right? Only one, so we have this already. Okay, so in test bench there will be two type of simulation. One is based on the text base, and another one is based on the what we call the timing, the graphical base. So now let's look at both simulation by using the timing diagram and also the text base. So to create the text base simulation, what we can do is this. We need to use the what we call the initial block. Yeah, remember last week when we go back to here, yeah, we have this, right? We learned this already as assign continuous statement for data flow modeling, always block for behavioral modeling. Yeah, in the quiz just now, we have get instantiation, module instantiation for the structural modeling. We have another one, right? Initial block, and I said that initial block is used for simulation, right? So in this case, now we use we do this for the simulation. Same as in always block, initial block, you need to have begin and end and your statement. Okay, if you have many statement, many lines of statement, but if you have only one line of statement, so you don't need the begin and end, right? So in my case, because I have only one line, so I don't need to have begin, right? So to create the simulation vector, what you need to do is you can do this, or to see, yeah, the simulation output. You use symbol this, yeah, the string monitor and we want to see D1, right? D1. Oh, I forgot this one. Before we do this, we need to instantiate this module in our design first, right? The example, the my design one in our case. So how to instantiate? Just like we use the module instantiation that we have learned last week. So the name is my design one, right? And give the name in this test as DUT. DUT is design under test, or you can use CUT, circuit under test, or whatever name you want to use, doesn't matter. So I always use DUT, design under test. Now we make a connection, yeah, just like this, just like what we have learned last week. To connect D1 to D1T is dot D1 connect to D1T, okay, separate by the comma, dot D2 connect to D2T, comma, dot D3 connected to D3T, comma, this A dot A connected to AT, right? Done. Now we have this design. Remember, this design name is my design one. Yeah, the name we call it DUT in the neo design, DUT, and then this is the testbench. Okay. Now we want to see in the simulation what is D1. So just like this is to print on the screen. Yeah, it is text based. Yeah, just like in C programming, when you learn C programming, if you want to print something on the screen, you use printf, right? So this is same thing. Monitor means that similar to printf in C programming. Okay, we want to see D1. We want to print D1, and D1 equal to what? Equal to in binary number. So this is how we display a binary number. Yeah, D1 in binary, %B. If you want to display in decimal, so %D decimal, hexadecimal is %H. Yeah. So D2 is also will be in binary. D3 will be also in binary. And A will be in binary, right? So it should be done. Okay, close that, separate by comma, and we need to link what is D1 actually. D1 is actually D1T. So D1T, D2 is actually D2T in this case, D3T, and AT. Okay, done for the initial. Okay, for the monitor. And now we want to create the input signal for D1, D2, D3. So how to create? If we have the 3 inputs like this, so we will have 8 input combination, 8 possible input combination, right? Starting from D1 equal to 0, D2 equal to 0, D3 equal to 0. and D1 equal to 0, 0, 1, 0, 1, 0 until we have all 1, 1, 1. We can create that in test code by using another initial block. Okay, and because we will have many statements later on, we now need a begin here. Begin. So now the time is very important. Let me show this. Okay, right? We want to create this. From 0 nanosecond here, 0 nanosecond to 10 nanosecond here, D1, D2, D3 should be 0. From 10 nanosecond to 20 nanosecond, we should have 0, 0, 1. And from 20 to 40 nanosecond, 30 nanosecond, we should have still 0 here, 0. Now we have 0, 1, 1. So this is 0, 0, 1, 0, right? Number 2, not 0, 1, 1. So it should be 0, 1, 0, like this. 0, 1, 0, and so on, right? So we want to create this. How to create this in Verilog? And Verilog, we cannot draw the timing diagram like this. We need to create the timing diagram using text-based to create this one, right? So how we do that? Go back to this. To create this at time 0, so at time 0, of course, the logic should be 0, 0, 0 at 0 time 0. So time 0, this is how we refer to time 0. Okay, so this is 0 second. Now the input D1, and D1 now is D1T. Okay, because we will fit the input into this D1T, right? D1T equal to 0. Done for D1T. So you can continue with D2 here, D2T equal to 0. But I think it's easy to continue like this. D2T equal to 0, D3T equal to 0. Easy for us to see, right? Because we have 0, 0, 0 to represent this 0, 0, 0. Okay, and next 10 nanosecond here, we want to change the value of the input, where in this case, let me copy this. Easy, right? Like this. So it should be 0, still equal to 0. This one is still equal to 0, but D3 equal to 1. So you can change this to 1. All right. Or if you are good enough, so you don't need this. Okay, because at 10 nanosecond, only D3 T is equal to 1 or change to 1. The others is remain the same. All right, remain 0. Okay, but for good view, easy to read, so I think right like this is easy, because we can see that 0, 0, 0, 0, 0, 1, and the next here 20 nanosecond. So we cannot write like this because the time here is accumulated actually. So if we write 20, actually it's referred to 0 plus 10 plus 20, which is 30 nanosecond. So here already. If we want to create a signal here at 20 nanosecond, what we need to do is, this is actually the next 10 nanosecond, because the time here is accumulated from 0 plus 10, so we have 10 nanosecond, plus another 10, we have 20 nanosecond, right? Remember that. Now at 10 nanosecond, we have 1010, right? Just like this. Sorry, at 20 nanosecond. So this is actually, let's comment, put a comment. This is 0 second. This is 10 nanosecond. This is actually represent 20 nanosecond, right? And another 10 nanosecond means that you add another 10 nanosecond, which is 30 nanosecond. You will have 1, right? This is for 30 nanosecond. And you can go on, okay, until you have reached 111. So this is number 4, 100. You have number 5, or 101. You have number 6, for 110. And you have number 7 for 111. Okay, when you reach this, for example, this is how this is 40 nanosecond. This is 50 nanosecond. This is 60 nanosecond, 70 nanosecond. All right. So what happened when you do this? Yeah, at 70 nanosecond. Let's say, for example, here is 70 nanosecond. 70 nanosecond. So what you get is that at 70 you have 111, means that this is 1 1 1 here, yeah, all logic 1 1 1 1. And when you finish here, for example, because we will end at 111, right? So you can write end here, begin and end. So what happened is that it will immediately stop the simulation at 70 nanosecond. What happened is that you cannot see the output, because there is no time already for you to see the output is changed from 60 nanosecond before to 70 nanosecond. So what we will do is normally to add to have time until 80 nanosecond to see what happened when we change the value at 70 nanosecond. All right, when we change the input at 70 nanosecond, and we have another 10 nanosecond to see the output. Okay, so to do that, what we need to do is to add another 10 nanosecond before we stop the simulation. So how to stop the simulation? The keyword is the money symbol and followed by stop. Okay, so this will stop the simulation at actually at 80 nanosecond. All right, so I think this is done. So we have the input, and we have the command to see the text, to see the output, and also we have the design, our design to test here. So it should be done. And module. Okay. So we have this already.
Sir,
Yeah.
maknanya kalau kita nak buat simulation tu, dia punya teori kena siap dah ada lah kan?
Theory.
Dia punya teori macam dia punya design dia apa semua dah kena
What
siap
do you mean
dulu.
theory? Means that your what do you call this one? Yeah, yeah. You need to plan.
Oh,
What is the input you want to put to fit in, to fit to your design. All right. We will see in detail in other example, for example. All right. So in this case, in this example, the input is 0000001 until we have 111, because our design we have only three input, so it's easy. If you have 4 input, so you need to have up to 16 input combination, right? Okay, so now we need to save our design. So let's save using this name. So let me copy this and I press save. And the suggestion is Verilog 2. No, we don't want to use this name. I want you to use my design 1TB. Save. Okay, I saved my test code already. So again, we need to check whether our test code is correct or not in terms of syntax. So we can use this feature also, analysis and elaboration. Click and let's see whether we have any error message or not. Okay, looks good. We don't have. So now we can run the simulation. So to run the simulation, we need to use the simulation software, which is the ModelSim. Right? This is the ModelSim. So you can run alone, standalone here by launching this ModelSim, or you can run from Quartus. My suggestion is to run from Quartus, because if you want to run separately using ModelSim or standalone using ModelSim, what you need to do is you need to create another project in ModelSim, right? But if you run from Quartus, you call ModelSim from Quartus, you don't need to create another project in ModelSim. Okay, so in this case I show you how to run from Quartus. So to run from Quartus, we need to do some settings by selecting this assignment. Go to setting. So you will have this window. So basically it will show there are many options here. You go to EDA tool settings, go to simulation, click this simulation, and you see this tool name, it says none by default. So you need to select the ModelSim Altera. So this is a must to do simulation whenever you have a new project. All right. So ModelSim Altera. Click this, compile testbench. Click this, test benches. You will have a new window. This. Click new. Another new window. Testbench name, so must be the same name as our testbench file, which is this file, my design 1TB. And then file name you add. Click this. So the file is my design 1TB. Click open. Click add. Make sure that this is listed here. Okay. Click OK, OK, and OK. Right. Now the setting is done. All right, click Tools, Run Simulation, go to RTL Simulation, click this, and we will launch the ModelSim. Okay, you can see in the tab here, the ModelSim is launching. Okay, this is ModelSim. It's launching now. So this is ModelSim interface. So you can go to transcript to see the output here. You can see the output. This is the output. All right, and we can check whether the output here is equal to what we have in truth table or not, right? So let's check. Okay, because this is very small. Let me capture this. Let me capture this. This is the output, yeah. Just copy this and then let's compare with what we have in in the truth table. Yeah, here, truth table, right? So let's see, we have 0, 0, 0. This is D1, D2, D3, 0, 0, 0. We have A equal to 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1. So it's correct, right? Exactly what we have in the... Now we can conclude that the design is correct because the output here, the simulation here is exactly the same with what we have in the specification or the truth table, right? Or also we can view the waveform. So this is a waveform window. Okay, in your case, if you don't see this, you can see wave here, waveform here. You click that in the tab, but my one I detached already. Wave is in another window, so you can tap the wave and see the waveform. So the waveform basically it not show all the signal at first. Yeah, means that you need to zoom in. So what you need to do is you need to zoom full to see the complete waveform from 0 to, in our case, 80 nanosecond, right? So this is the waveform. This is difficult to see, so you can click this, yeah, toggle leave name such that you can see this only D1T, D2T, D3T, 80. You can see here 0, 0, 0, 0, 0, 1. So the output is 0, 0, 1, 0, and so on until you have 1, 1, 1, and the output A equal to 1. So you can see that we end the simulation at 0.0 microsecond or at 80 nanosecond exactly. All right. So this is based on our test code. So you can see that if you have something like this, yeah, 3 input, 1 output. So the best way to verify your design is to use, I think, text based is easier because you can compare straight away to your truth table. But some of or many cases, yeah, some of the cases, actually many cases, we need to use the waveform, right? For example, when we design the full RTL later on, when we learn the sequential design later on, so it is better to use the waveform as compared to the text based like this. But combinational circuit text based is it's quite easier for us to see. Okay, I think I forgot one thing for you. If you follow this tutorial exactly from step to step, step by step, I think you will face one issue when you want to do simulation, because I forgot to tell you one thing. Because in my Quartus, I use this many times already, but for you as a first time user, what you need to do when you want to do simulation is that you need one other setting. This is one time setting only, because just now I said that we want to run the ModelSim from we want to run ModelSim from the ModelSim from the Quartus. So what you need to do is you need to link that Quartus, our Quartus, to ModelSim. So how to do that? What you need to do is you need to go to here, tools. This is one-time setting, right? Tools. You go to option, okay, and you will have this window, okay. You go to this EDA tool option, and by default, yeah, this one is actually empty. By default, this one is actually empty, like this, in your case, right? So you need to link your ModelSim to ModelSim Altera, this one, yeah, not this ModelSim Altera, the one that we use, the one that we install. You need to link your Quartus to ModelSim Altera, yeah, or you need to tell your Quartus that where is this ModelSim Altera. So to do that, you go to this, go to your install. Where do you install your Quartus? So in my case is here, this version 20.1. You go to this ModelSim ASE, okay, click this, and you go to Win32A-LOEM, click this, select folder, such that you have this. Okay, so when you have this, then just click OK. This is done, right? If not, you cannot be able to launch the ModelSim from Quartus. It will show you error, meaning that it cannot find your ModelSim, right? So with that, you can do simulation from Quartus. Okay, I think that is the tutorial that you can do, and you can test up until now, until chapter 2, right? So chapter 2, there will be a lot of tutorial question. So I think you can try to do this tutorial. Okay, like for example, number 3, number 4, write Verilog program to create this circuit, and then write testbench to verify the functionality of the circuit in question 4. So I think this is maybe your exercise. Okay, your exercise, and we will discuss this after the break. Okay, also I think during the break, I will give you the first assignment 1, okay, based on what we have learned so far, and also to get you familiar with the Quartus software and also do the simulation. All right, and this tutorial question also is a good exercise for you, yeah, before you can do your assignment. And remember, assignment is very important, 30% of your coursework mark, right? So please, yeah, focus and do your assignment. Okay, all right, there are a lot of questions, so you can try to do. Okay, any questions so far?
No.
Okay, so if no question, I think we will end the class session here, and I will give you the assignment by the end of the week. Okay, see you next week. I mean, after the break. Happy holiday and happy Deepavali for those who celebrate the Deepavali.